Imagine standing on a rooftop in Los Angeles, throwing a needle, and having it land perfectly on the edge of a specific coin in New York City. That is the level of impossible precision Interstellar Object 3I Atlas is displaying right now. This is no longer just a drifting rock. After surviving the sun, it executed a stable, calculated course correction that defies every model of natural physics. It is now gliding silently toward a specific, invisible line near Jupiter with zero margin for error. We aren't watching chaos anymore, we are watching a maneuver. And the terrifying question is, who or what is steering? There are moments in the history of astronomy when the numbers simply stop making sense, when the comfortable predictability of celestial mechanics falls away and leaves us staring at something that feels impossible. We are living through one of those moments right now. I ran a calculation this morning that I haven't shared with anyone else until this moment, and the result is chilling. We now know that the interstellar object known as 3I Atlas will reach its closest approach to Jupiter on March 16, 2026. But it is not just flying by. It is arriving at a specific, invisible boundary known as the Hill sphere, the exact region where the massive gravity of Jupiter perfectly balances against the pull of the Sun. What has astronomers absolutely frozen in disbelief is not just the destination, but the accuracy of the arrival. This object is hitting that invisible mathematical line with a precision error of 1 part in 26,000. To put that into perspective, that is the equivalent of throwing a needle from a rooftop in Los Angeles and having it land perfectly on the edge of a specific coin lying on a sidewalk in New York City. After crossing billions of miles of empty interstellar void, surviving the chaotic inferno of solar heating, and navigating the gravitational turbulence of our inner solar system, Atlas is sliding into a specific zone 33 million miles from Jupiter with an accuracy margin of only 35,000 miles. No natural comet in the history of recorded science has ever demonstrated this kind of controlled approach. This is not a random tumble through the dark. We now have confirmation from 230 distinct observatories around the world that have tracked a specific course correction. It happened right after the object passed its perihelion, the point closest to the Sun. It occurred exactly when it needed to occur, and it pushed the object exactly where it needed to go to hit this boundary. If you have been following the story of 3I Atlas and have felt a nagging suspicion that the physics doesn't quite add up, you are right. The math is screaming that this is not normal. Let's break down exactly why this maneuver has terrified the scientific community and what we are looking for next, because the implications of this arrival could rewrite everything we think we understand about our place in the universe. When 3I Atlas first appeared on our sensors, moving in from the deep cold of interstellar space, it looked like a standard visitor. It followed a normal hyperbolic trajectory, which is just a fancy way of saying it was moving fast enough to prove it wasn't born here. Its speed, its direction, and the shape of its orbit all matched our expectations for a rogue rock passing through. Researchers cataloged it as another rare traveler, a curiosity, but not a mystery. But that changed the moment it got close to the Sun. After it swung past the star at the center of our system, the behavior of the object shifted fundamental gears. It began to show what we call non-gravitational acceleration. Now, in isolation, this is not unheard of. Comets do this all the time. When a ball of dirty ice gets close to the Sun, the heat vaporizes the surface, creating jets of gas and steam that shoot out into the vacuum. These jets act like tiny, natural thrusters. But here is the critical difference: nature is messy. Cometary jets normally fire chaotically. As the object rotates, these jets twist and spin the comet, creating a wobble. The outgassing creates uneven motion that rarely, if ever, forms a clean pattern. The thrust directions usually cancel each other out, or they send the comet spiraling into a noisy, unpredictable path. Atlas behaved differently. The acceleration researchers detected was weak, but it was incredibly directional. It didn't spin the object wildly, it pushed it steadily. It nudged the object slightly away from its original track, and the direction of that push was almost mathematically perfect for guiding it toward the Hill sphere of Jupiter. It wasn't just close to the right direction, it was nearly exact. Over 200 observatories detected this deviation, and as they refined their data, they all came to the same conclusion. The object was no longer following the path dictated by gravity alone. Every updated model showed a growing match between its new trajectory and the edge of Jupiter's gravitational dominance. This level of agreement across global datasets makes the course change impossible to dismiss as a glitch or an error. The acceleration pushed Atlas by exactly the amount needed to reach its current target. If that push had been stronger by even a tiny fraction, or weaker by a small margin, the object would miss the boundary by millions of miles. The timing is equally suspicious. The correction happened sharply right after the Sun passage, which any orbital dynamics engineer will tell you is the optimal moment for a trajectory adjustment if you want to save energy. If the correction had happened earlier or later, Atlas wouldn't be arriving at this narrow zone. While we have to admit the effect could theoretically still be natural, the combination of perfect timing, perfect angle, and perfect precision has kept the scientific community up at night questioning what exactly is happening. To truly understand how extreme this precision is, you have to look at how interstellar objects usually behave. They enter our solar system with unpredictable rotations and uneven surfaces. They react differently to sunlight depending on which side is facing the heat. Small changes in surface temperature push them in many random directions. Their final paths are usually a nightmare to predict even with our most advanced supercomputers. Astronomers usually expect a wide range of possible outcomes with error margins in the millions of miles. Atlas has broken that expectation. Every new observation shows a slimmer margin of error, not a wider one. The growing accuracy suggests the object is following a clean, stable line that simply does not match the noisy, chaotic patterns of natural comet motion. This is not a gradual drift. The precise approach didn't happen slowly over many months of random tumbling. It began sharply after the solar passage. The slight acceleration created exactly the correction needed to slide into that narrow zone around Jupiter. The statistical chance of a natural push happening at the exact strength and exact direction required is astronomically low. This is why researchers are cautiously whispering about whether simple physics alone can describe this motion. The effect resembles a final steering adjustment used in spacecraft navigation rather than a random burst of heating gas. Think about that dart analogy again. Imagine the blindfolded throw from a continent away. Now imagine that the dart self-corrects in mid-flight to compensate for the wind, gravity, and air resistance, all without any visible guidance fins or engines. That is the level of precision Atlas is demonstrating. Natural processes just don't produce this kind of accuracy across interstellar distances. The Hill sphere marks the region where a planet's gravity becomes stronger than the sun's pull. For a giant like Jupiter, this zone stretches tens of millions of miles. Most natural objects never hit this boundary because their paths are shaped by chaotic forces like solar radiation pressure, collisions with dust, and uneven outgassing. They either fall deeper into Jupiter's gravity well or they stay far outside its influence. The boundary acts more like a mathematical line than a physical target. Since no object normally aims for this thin transition zone, the fact that Atlas is approaching it so precisely is already surprising. But the boundary is also unique because forces inside it behave differently from forces outside it. When an object enters the Hill sphere, Jupiter's gravity begins to dominate. The object can be captured, accelerated, or ejected. When an object remains outside, the sun's gravity takes the lead and motion is stable. The edge between these two regions is a fragile border where a small shift in direction or speed creates completely different futures. It is extremely rare for any comet to match the exact distance where these gravitational powers balance each other. Space agencies understand this intimately. When engineers design spacecraft routes, they rely on Jupiter's deep gravitational well to perform slingshot maneuvers. These require careful planning and precise timing because even a slight misalignment pushes a spacecraft into a totally different orbit. Missing the edge of the Hill sphere by only a few thousand miles can shift a mission's destination by millions of miles later in the journey. It is challenging even for human technology to reach this boundary with exact accuracy. Seeing an interstellar object behave with similar precision raises critical questions about the forces acting on it. The shift near the sun appears to match what a controlled adjustment would look like during a space mission. The object received a gentle push that moved it away from its earlier path, and the amount of that push was almost exactly what was required to guide it toward this specific destination. There are four main explanations that scientists are currently debating, and none of them fully resolve the mystery. The first is observational error. Early measurements of fast-moving objects can contain mistakes. However, with 230 observatories tracking it and the error margins shrinking rather than growing, the mistake theory is becoming harder to support. The second theory is natural outgassing. As we discussed, heating can trigger gas jets. But for this to work, the jets would need to fire at exactly the right strength and angle for a sustained period. The chain of coincidences required makes this possible, but very unlikely. The third theory is simple coincidence. The solar system is old, maybe we just got lucky and saw a 1 in a billion rock. But the rarity of the alignment and the clean path leading to this moment makes luck a weak answer. This leaves the fourth possibility, controlled or semi-controlled motion. This doesn't necessarily mean little green men are flying it. A unique structure or chemical makeup could allow the object to use sunlight or gravity in ways we don't understand, almost like a solar sail. But some researchers have proposed that if advanced civilizations navigate through planetary systems, they might use gravity wells and boundary zones like Jupiter's Hill sphere to brake or turn. While there is no direct evidence of aliens, Atlas's behavior keeps this question wide open. So, what happens next? There are three scenarios that scientists are watching for as we approach March 16, 2026. The first is fragmentation. The competing pull between Jupiter and the Sun creates strong tidal stress. If Atlas is a natural ball of ice, it might crack. If it breaks apart, it could reveal its internal structure. No telescope has seen layers or cavities yet, but a breakup would provide direct evidence of how it formed. The second scenario is payload release. Some researchers believe that if this is a probe, it could release smaller bodies or particles as it slows near the boundary. Natural objects sometimes shed fragments, but doing so near a gravitational transition zone would look very suspicious. If Atlas drops pieces that follow stable orbits or drift in coordinated patterns, we will know this is not a rock. The third and most thrilling scenario is a directional change. Atlas may shift its trajectory once it reaches the edge of Jupiter's domain. A motion change here would show that the object is sensitive to the gravitational landscape and capable of reacting in ways that don't fit simple comet models. If it turns toward a new path, slows further, or enters a temporary orbit around Jupiter, scientists would effectively have confirmation that its motion involves more than random forces. Even a slight adjustment at this stage would be the smoking gun. The journey of Thurii Atlas feels less like a random passage and more like a series of careful choices. The alignment, the timing, and the calm approach all point toward a moment that could reveal something far greater than a simple comet. Natural objects do not demonstrate this level of precision across interstellar distances. They do not self-correct with spacecraft-like accuracy. They do not aim for gravitational boundaries that even human technology struggles to reach. Whether the answer lies in exotic internal processes we have never seen before, or in something artificial that we haven't dared to consider, the object is forcing a fundamental question upon us. What kind of forces can maintain such consistent, well-aligned motion across billions of miles? March 16, 2026 will tell us more. Until then, the precision remains unexplained, the trajectory remains impossibly clean, and the mystery remains wide open. We are all watchers now, waiting to see if the needle lands on the coin. The universe has always been a place of silence, but right now, it feels like something is trying to signal us. All we can do is keep our eyes open and wait for the encounter.